Hello everyone, welcome back to my channel. I'm Nandini. Today I'm going to discuss about breadth first search under the subject Principles of Artificial Intelligence. First, let us see the introduction to the breadth first search. Breadth first search is a graph traversal algorithm. It's used to explore and analyze the vertices and edges of a graph in a systematic and comprehensive manner. Unlike depth first search, which explores as far as possible along each branch before backtracking, BFS systematically explores the vertices and edges by starting at the root node and visiting all its neighbors before moving on to the next level of the graph. This algorithm is widely used in the various applications such as finding a shortest path in graph-based data, network analysis, and social network analysis and puzzle solving. Its simplicity, completeness, and optimality for unweighted graphs make it a fundamental algorithm in the field of computer science and graph theory. Next is a definition and purpose of BFS. Breadth first search is an algorithm used for traversing a searching tree or graph data structures. The main purpose of BFS is to systematically explore and visit all the nodes of the graph that are reachable from the given starting node. It iteratively visits neighboring vertices of a current vertex and continues the process until all vertices are visited. By using a queue data structure, BFS explores all the nodes at the present depth before moving on to the nodes at the next level. This approach makes BFS particularly used for finding the shortest path between two nodes in an unweighted graph. Additionally, BFS can be adapted for the use in the various applications such as finding the connected components in the graph and testing if a graph is bipartite. And next, let us see the how BFS works. Breadth first search is an algorithm used to traverse or a search tree or a graph tree structures. It starts at the root node and explores all the neighbor nodes at the present depth before moving on to the nodes at the next depth level. This approach ensures that all the visited nodes closest to the root node before moving on to the nodes that are further away. And the algorithm using a queue data structure maintains a list of all the nodes that are yet to be visited, ensuring that the nodes are visited in the order which they are discovered, and it also continues this process until all the nodes in the search space have been explored. And one of the main key aspects of the BFS is that it is a guarantee to find the shortest path between the starting node and any other reachable node in an unweighted graph, and this make it particularly useful for pathfinding algorithms and network analysis. Next, let us see the implementation of the BFS algorithm step-by-step process. In the implementation of the breadth first search algorithm, the process begins by visiting a starting node and then systematically exploring all of the adjacent nodes. This exploration is conducted level by level and ensuring that all nodes at the given level are visited before proceeding to the next level. And next is the queue data structure. The key to the BFS algorithm lies in the use of queue to manage the order of node exploration. As nodes are visited, they are added to the queue and the algorithm continues to pop nodes of the queue, visiting their adjacent nodes and adding them to the queue as well as. Next, optimization and variations. There are various optimization and variations of the BFS algorithm, including techniques for avoiding revisiting nodes, handling disconnected graphs, and adapting the algorithm for specific use cases, such as finding the shortest path in the unweighted graph. Next, let us see the time and space complexity of BFS. Time complexity O of V plus E, space complexity O of V. Breadth first search has a complexity of O of V plus E, where V represents the number of vertices and E represents the number of edges in a graph. And it explores all the vertices and edges of the graph in the systematic manner, moving level by level. The space complexity of BFS is O of V, as it requires space proportional to the number of vertices in the graph to keep track of visited vertices and the queue used for the traversal. And due to the linear time complexity with the number of vertices and edges, BFS is efficient for searching and traversing unweighted or uniformly weighted graphs. The space complexity, though linear, can be limit for the larger graphs when memory resources are constrained. Let's let us see some of the applications of BFS. Social network analysis. BFS is widely used in the social network analysis to determine the shortest path between the individuals or entities, identify clusters of closely connected individuals, and analyze the overall structure of the network. Routing and networking. In computer networking, BFS is employed to discover the shortest path between nodes in the network, and which is crucial for efficient data packet routing and improving overall performance and network communication. Puzzle solving. BFS is used in puzzle solving algorithms such as Rubik's cubes and other permutation related problems to find the shortest sequence of the moves to reach a solution, make it an essential technique in the recreational mathematics as well. Next, let us see some of the advantages and disadvantages of BFS. Advantages of BFS is BFS is particularly useful in finding a shortest path in an unweighted graph. It guarantees the shortest path unlike depth first search. Additionally, BFS is capable of visiting and searching all the nodes, which is beneficial in scenarios where complete traversal of a graph is required. It is also easy to implement using a queue data structure. Next is the disadvantages of BFS. One of the major drawbacks of BFS is its need for more memory as compared to the depth first search, and this is due to the fact that BFS needs to store all the child pointers at the same time, which can lead to memory limitations in large graphs. Furthermore, BFS might not be in the best choice for systems and which is limited memory and computational power due to its higher space complexity. Next, let us see some of the steps for the how BFS works. First step is the initialization. The first step in the BFS is to initialize a queue and mark the starting node as visited. And second step is the explore neighbors. Next, the algorithm explores all the neighbors of the starting node and adds them into the queue. Depth queue and visit. The algorithm depth queues a node from the queue, visits it, and then explores its unvisited neighbors, adding them into the queue. Next, last step is the repeat until complete. These steps are repeated until the queue is empty and all our reachable nodes are visited. Next, let us see the relation between BFS for graph and tree traversal. When it comes to the traversal algorithms, breadth first search serves as a foundational concept for both graphs and trees. In the case of graph traversal, BFS systematically explores the nodes of a graph level by level, ensuring that all the nodes of the certain depth are visited before moving on to the nodes at the next level. It guarantees that the shortest path between two nodes is discovered, making it highly useful for the applications like finding the shortest distance between two nodes. On the other hand, when applying BFS to the tree traversal, it shares similar principles. The algorithm starts at the root and explores all the neighbor nodes at the present depth, moving on to the nodes at the next level. This approach ensures all the nodes at the current level are visited before moving down to the next level, making sure that the nodes are visited in the order of their depth from the root. This can be particularly useful in scenarios like hierarchical data representations and search operations with a tree structure. While the fundamental principles of BFS remain consistent across both the graphs and trees, the specific implementation and application may vary based on the nature and characteristics of the given graph or tree. Understanding the relationship between BFS for graph and tree traversal provides a strong foundation for comprehending traversal algorithm and their diverse application in various computational tasks. Next, at last, let us see the conclusion. As we conclude that our exploration of breadth first search, it's important to note the significance of this algorithm in various applications. BFS is a foundational concept in computer science, utilized in solving a wide range of problems, from finding a shortest path in a graph to analyzing network connectivity. Its simplicity and efficiency make it a valuable tool for many programmers and software developers. Furthermore, the understanding of BFS provides a strong foundation for tackling more complex graph algorithms and data structures with its emphasis on exploring all neighbor nodes at the present depth Before moving on to the nodes at the next level, BFS offers a unique approach for problem solving that sets it apart from the other search algorithms like depth first search. So thank you for watching. Please do like, share and subscribe.